Hi, can you hear me?
Yes, sir.
Okay. Okay, let us start. So today I think we can complete the cross ratio topic. There are a few problems remaining, so we can go through them. And what I'm planning for next time is actually a small test for you based on the two topics we have done so far, which is the power of a point and cross ratio. And most likely, what I will do, I'll have two sections in the test. One will be numerical, like from like PRMO pattern 00 to 99 numerical answer, and there will be at least two or three questions which will be long form where you have to like prove that something, you have to write out the solution properly. So I'll give you practice for both of them. And I mean, this is a test mainly for each of us to understand what are our strengths and weaknesses in both types of problems. Like somebody may be good at doing the calculations correctly, but they may struggle with writing the long form answers or vice versa. And also for you to keep a check on your revision habits, that are you able to remember what we did 2 months ago. So for all those reasons, I think it is good to have a test once in a while. So next Sunday, I'll have to plan out whether I want to give you the test a full 2 hours, or maybe we can have the test for 1.5 hours and keep the remaining time for discussion. So I will figure it out. But anyway, I mean, just to let you know that I think next Sunday we will have this test. Okay. So coming back to the problem sheet. So we did up till problem B last time. Actually, problem A and B I skipped, but I hope they are simple enough that you can figure it out. So I'm not going to spend my time on the easy question A and B. And C and D we already did. So from E onwards, E, F, G, H, these four questions we have to do. And also, I mean, let me take the time today to walk through some small things. I think I have missed once in, somewhere here or there while talking you through the theory. So whatever small things gaps are there, let me just complete all the theory topics for that. Like for example, here I think there is one thing which I didn't mention last time is the harmonic quadrilateral. So let me just talk about that. And also in the power of a point and cross this coaxial circles, let me just think if there are any couple of minor points which I missed to mention while doing the theory. So I just want to round out both these topics today also. So that's why I won't start inversion. Even if we complete these problems early, I don't want to start a new topic today. We will do that after the next time's test is done. Okay, so question E, can you raise your hand if you already have solved question E? Okay, Jaydeep has solved. Anybody else? So for those who are not solving these questions, either I mean you don't spend enough time to attempt these questions, or you are getting stuck somewhere. So I want to help you out. I mean, I don't want to just reveal the solution every time, because that will be of no use to you. So I want to understand from your point of view that what is it that you are not able to get. So for that, I mean, it would be great if even if you don't get the full solution, just explain to me what is your attempting. Where did you get stuck? What are the things that you're able to see in a given problem? So if you give me that kind of insight, then I can help you out. And I mean, basically it might be just a small one-line hint where you are stuck. That if I tell you that hint, the rest of the problem you can do on your own. So I mean, I don't want to reveal the solution directly without giving you a chance to try it properly. So for that, I mean, in the classroom, this is much easier because I can go around on each person's desk and see their notebook. That gives me the idea that where you are stuck. But in Zoom, that is not possible, unfortunately. But yeah, so you have to speak out and tell me that this is what I could get and this is where I got stuck. So what I'll do, I'll start by drawing the diagram and then I'll let you, somebody of you, explain what are the things that you can see, what are the properties you can see. And of course, those who have already solved this question, Jaydeep or anybody else, will let others a chance to explain what is their difficulty. What is it that they are not able to see in this question? Okay. So given a non-intersecting coaxial family of circles. So first thing for everybody to understand, do you understand what this phrase means? Because we have been using this phrase many times. And so I hope it is clear what is the picture you're supposed to draw when you read this part, given a non-intersecting coaxial family of coaxial circles. What is the diagram that you're supposed to draw? So the first thing that is given is the limiting points A and B. So in a non-intersecting family, the limiting points are also part of the coaxial family, except that they are circles of point 0. So let's say these A and B are the limiting points. Okay. And now let line AB intersect any circle of the family at points C and D. So I want to draw any arbitrary member of this family. So first thing is that for all the circles of this coaxial family, what is the common radical axis?
Perpendicular bisector of AB.
Perpendicular bisector of AB. Okay. And again, if you're not able to remember this, just go back to the theory. Understand what is this family of coaxial circles. It is nothing but the Apollonius circles with different ratios. So if you choose the ratio k equal to 1, then it is the perpendicular bisector. But if you choose any other ratio, then you'll get a circle like this. Okay. So every point on this circle has some Apollonius ratio, some k, and it is intersecting this line AB at points C and D. And now the question is, points AB and CD are harmonic. This is what I have to prove. Okay. So for those who did not solve this problem, start thinking aloud that what is the meaning of this? What is the meaning of the harmonic? Can you rewrite the same thing in some different way? In fact, we have seen this property many times already. I mean, the previous question was also very similar. So there's nothing new here. In fact, I just gave you the answer. When I said that this is Apollonius circle, that itself should tell you the answer now. So if this is the Apollonius circle, which means every point on this circle has a constant ratio, right? AP upon PB is some constant K.
Yes, sir.
And what about point C and D? Will point C and D also have the same property?
Yes, sir, but with opposite sign.
Opposite sign, correct?
Negative.
That's all right. I mean, there's nothing more to be done. This is exactly what we mean by the points are harmonic. If I take everything to one side, the cross ratio will be -1. So, I mean, there was actually nothing in this question. It was only about the question never said Apollonius circle. That was the only tricky part. It said non-intersecting coaxial family of circles. So that is where, I mean, your revision or your ability to connect these ideas is important. That knowing how we constructed this non-intersecting family, it should be clear to anybody that this is the family of Apollonius circles. So then once you identified that part of the question, there is nothing more to be done. Okay. So again, for those who are not able to see these things, I want you to take the time to understand the thought process. I mean, the final solution is not the important thing, but the thought process, how you arrive at this part. Like, what are the steps you are supposed to do to get this solution? That is what you should be focusing on. So here the most important step is to reword the phrase coaxial family into Apollonius circles. So once you do that, the rest is doable. Okay. And you'll see this many times. Basically, in geometry, the same diagram can be unpacked in so many different ways. Like you may already have some experience of this, like the orthocenter configuration, triangle ABC is also the incircle excircle configuration if you look at it from the perspective of the inner triangle DF. So the same diagram has multiple perspectives to it. This happens all the time in geometry. So you have to exploit that fact and choose the right frame of reference. You can say that which is your main triangle ABC, and then the whole diagram is interpreted in terms of that starting triangle. Okay. So question F. I think for this question, maybe you need the definition of harmonic. Let me just draw the diagram. Okay, no, you don't need it. So this is the question now. There is a point P outside the circle, and you are drawing the tangents A and B. Okay. Then the segment AB, so line AB rather, and there is another line passing through point P, which intersects the circle at point C and D, and this line AB at point Q. So the question is P, Q, and C, comma D are harmonic. So how can we do this problem? First, let me draw the diagram again because PA and PB is supposed to be equal in length, but doesn't seem like that in my diagram. Yeah. So actually, this is a very interesting question, and you will find this question once more later on when we do the topic called poles and polars. So this is going to come back to us many times. This diagram, as it turns out, the line AP is called the polar of point P, and so on. So there are a lot of cross corrections with this question and the topics which are going to come after inversion. So the part which we have to prove that P, Q, and C, D are harmonic. We can rewrite this in a number of ways now, and we have to pick which of the possible ways to rewrite might be the most useful to solve this problem. And it could be that there are multiple solutions, that there is not only one way to do it. But the most straightforward definition which we want to follow, for example, could be the ratio of the two segments. So, for example, we could be looking at CQ upon QD, and if we prove it is equal to minus of CP upon PD, we are done. And so this is from the perspective of what we have to prove. But we also have to look from what is given to us, because there is a lot of information given to us. The fact that PA and PB are tangents. Okay. So given PA, PB are tangents. So then that allows us to do a lot of angle chasing, things like that. So for example, if I consider this, if I draw these segments, okay, then do you see by tangent secant theorem, I can have a lot of similarities. So what are the various similar triangles that you can see here? Or rather, first, even before looking at similar triangles, let us look at what angles can be changed. So for example, I can see this angle is equal to this angle by tangent secant theorem, and that is also equal to this angle. Similarly, I can, by symmetry, I can do the same thing for the other side also. So basically this angle, which equals this angle. So which similar triangles can you see? For example, triangle PAC is similar to what?
So PVC. PVC.
PDC, correct? Sorry, PDA. Why PVC? Not PVC, right? PDA. Because of the red angles which I marked just now. See, finally, we are interested in the ratios given below, CP upon PD and CQ upon QD. So we have to think of triangles which are connected to those values. We are not interested in any arbitrary triangles for now, but these ratios in particular are of interest to us. Okay, so triangle PAC is similar to triangle PDA. So that allows us to write some ratios like CP. What does that allow?
So even triangle CBQ and CDA are similar.
CBQ is similar to triangle C. Which is the other triangle which you mentioned?
QDA.
QDA, correct.
Triangle QDB is similar to QAC.
QDB is similar to QAC, correct? So, I mean, there is a lot of similarities here, but we have to be careful in picking which of the triangles will give us something useful. Because, I mean, for example, this one, right? The first one which I wrote.
Sir, PBC is similar to PDB.
PBC is similar to PDB, correct? So out of all of these triangles, which one should be used? Because the difficulty is, a lot of these triangles, if you recall, are used in the proof of 4 of a point. So if you try to write out the ratios, you might get things such as CQ into QD equal to AQ into QB, which we all know, which is the power of the point. But the difficulty is we are interested in the ratio CQ upon QD, not the product. So that is why I think we have to be careful in choosing the right triangle here. Okay, do you understand the difficulty?
Yes, sir.
Yes, sir.
Because I mean, even if you look at the first triangle, this first pair which I wrote, right? If I try to write the ratios, because I'm interested in the CP upon PD part, what will I get? PA upon PD equal to AC upon DA equal to PC upon PA. So if you see, if I cross multiply the terms, I'm not getting CP upon PD, I'm getting CP into PD. So how do we solve this problem? Okay, let us look at it from a different way. Let us consider the ratio CQ upon QD. Okay. I don't know whether these similar triangles will help us or not right now, but it's just good to know them. So I'm just going to write the similar triangles and leave it at that. Which ratios we use when we'll come back to that later, but let us take a different approach. CQ upon QD, there is another way in which we can rewrite these ratios, which is using that property from earlier. Basically, whenever you have a in triangle ACD, you see that CQ upon QD can be written as the ratio of the sines of the opposite angles. So in triangle ACD, what can we write? What is CQ upon QD equal to? So the angle which I am talking about is the orange angle which I have marked, and this angle, this blue angle. So what is
Sin QAC upon
So CA
AD
into
sin
sin QAC upon AD into sin DA.
correct? So CA upon AD into the sine of angle QAC upon sine of angle QAD. Or let me just write CAQ. I have to keep the order conserved. This is CQ upon QD. And so if I call this statement 1, and I'm interested in CP upon PD also. So CP upon PD can also be written in the same way. What will that be equal to? So for Cp upon Pd, the only thing that will change is the magnitude, or rather the angles, signs of those angles. So here CAQ, instead of that there will be CAP on sign of angle PAD. Okay. So if we were taking directed angles and ratios, the Cp upon Pd ratio will be negative, and in the angles will also, one of them will be negative. So everything will be taken care of automatically by the directed quantities. So if you see what this is telling us to do, we want to show that these are equal to each other, minus of each other. So what is equivalently, what is that we have to prove? Because Ca upon AD is going to cancel out, right? So what is it we have to prove really? We have to only prove that sine of CAQ, basically just the sine part will survive. Sine of CAQ upon sine of QAD equals sine of this is all we have to prove.
Then the RHS should be negative.
Oh yes, RHS should be negative. Okay, so let me just fix the RHS negative part by flipping one of the signs. So instead of writing sine of angle CAP, I'll write PAC. Okay, so then that will fix the negative sign. So now I can talk about positive angles. Okay, so yeah, we have made some progress, but we still have to find out we have to figure out how to prove this quantity. But this blue angle and this blue angle are equal. And so basically if I mark the colors, the angles which we are interested in here, and I will need lots of colors, but still. So what are the colors? Sine of angle CAQ, which is orange. So orange upon blue equal to PAC, which is red upon purple. Okay, do you see the angles, the colors of the angles? CAQ is nothing but orange. This is orange. QAD is the blue color. PAC is red. And PAD. So PAD is the if you say it is red plus orange plus blue, but I can take it supplement because sine angles is sine of x and sine of 180 minus x is identical. So instead of that, I have taken the external angle, this purple angle, and by tangent secant theorem, you see this angle is also equal to ABD.
Yes.
Okay, so this is what you want to prove: orange upon blue equal to red upon purple. Okay, so this is how I can see we can do this. Now, there may be a better way or simpler way, but at least this seems to work. So the idea is this. First, I want to locate where I can find these colors and where I can use some of the known quantities. For example, orange upon blue, right? If I can, if I look at triangle BCD, for example, in triangle BCD, do you see by sine rule, orange upon blue is nothing but the opposite sides.
Yes, sir.
So then what is the LHS? What can we write? Orange upon blue is equal to, basically orange is angle CDB and blue is angle DCB. So the opposite sides are BC upon BD. And what about red and purple? Do you see red and purple in the triangle CAD?
Yes, sir.
So then this is CA upon
AC upon.
AC upon AD or CA upon AD, anyhow. So this is all we have to prove, BC upon BD. So you see how we are keeping on converting the information into something else that we can prove. So instead of the sign, this looks much easier. BC upon BD equal to CA upon AD. If we prove this, we are done. And now I think all the similar triangles that we noticed before, we could try using some of them now. Because now, because everything is terms of ratios, the signs have gone away. So now we can figure out, for example, BC and BD. Do BC and BD belong to any pair of similar triangles?
The second one.
Sir, the second
The
one.
second one.
Second one. Okay. And I think CA and AD belong to the first pair, right? So let us see what happens if we write out both the ratios. I hope it works actually. Even I don't remember this solution, how I did it previously, like last year. But it is something like this only. So let us work it out. So the first part, if I write it out, it is PA upon PD equal to AC upon DA equal to AC upon PA. And the second one, PB, so PB upon PD equals BC upon PB equal to BC upon. Okay, so is this helping us? I think it is finishing the problem. Do you see that? Why is it the case? Because
PA is equal
Yes, so PB and PB are
PA and
equal.
PB are equal, exactly.
Yes, sir.
So the things which you want to prove are this. So you want to prove this is equal to this. But the first term, PA upon PD and PB upon PD are clearly equal because PD and PD is equal and PA equal to PB. So therefore, this is true. And I mean the RHS term could also give the same thing, PC upon PA and PC upon PB. Okay, so let us walk through the solution once again because there are quite a few steps that we did. I mean, ultimately the actual solution is only this big. It is not like previously we were exploring ideas, we were writing out similar triangles because we didn't know where to go. But after we found some direction that, okay, we want to write the ratio CQ upon QD in a particular way. And if you notice throughout, the focus was on cancelling things or simplifying things wherever possible. So like the first step itself, when we wrote CQ upon QD, I used triangle CAD. Then for CP upon PD, I again use the same triangle CAD because then that allows these ratios to cancel out. Okay, then once you get that it is purely in terms of the signs of the angle, now we want to see how we can rewrite that. We have to make use of all the equal angles in the diagram. Okay, so this orange, the CAQ and QAD, there are so many choices which angle you choose, and probably if you ask me, right, there are so many other choices which will also give you valid solution. Like maybe some other property can be used, but the one which we found the simplest was the sine rule. So we found the triangles where the both angles are occurring in the same triangle. So for orange and blue, we found triangle BCD, and for red and purple, we found the triangle CAD. And again, if you see the symmetry seems to help, and BCD and CAD, they are symmetric with respect to this line. So that I think helped us. And then the final step was the similar triangles which we had spotted earlier. So I mean the whole problem revolves around finding equal angles, similar triangles, things like that. Okay, but now I'm trying to think whether last year when I shared this problem, this was the same solution or not. I think there was a slightly different solution back then, but if it comes back to me, I will let you know. Otherwise, at least this one solution we have. Okay, any doubts in this question?
No, sir. No, sir.
Okay. But let me just explain why this property is very important. I mean, this is not just a question or a problem for a practice, but this is going to be a important thing which we derive later on when we use poles and polars also. And actually, poles and polars are quite a interesting branch of mathematics, I will say, because it is not just confined to this circle. In a projective geometry context, there is this term poles and polars comes up in a lot of different areas also. So, how do I explain? Okay, let's redraw this diagram in a slightly different way. Okay? I mean, it's the same diagram, but our starting point will be slightly different. So what I'll do is this: I have a circle and a point P. Okay. Now I draw any random line through point P. Okay. So it will meet the circle at points C and D, like we did before. Okay. So from the question that we did just now, if I take the harmonic conjugate of point P, which is to say the point Q, such that P and Q divide CD internally, externally in the same ratio. Okay. And now I allow, so point P is fixed, but this line is varying. So I could choose a different line, for example, which will give a point C1, D1. And on that line, I'll get a point Q1, let's say. So as I change this line, the point Q keeps moving, right? And so what we have proved just now is that the locus of the point Q is a straight line, because on this point Q and Q1 always lie on the that line AB, where A and B are the points of the tangency. Okay, so the point this Q and Q1, as the line L moves, this point Q also moves on the straight line. But I mean, in this diagram, it may seem that we have to stop at the two ends of the vertices, segment A and B, because obviously, if you take a point line through point P which does not intersect the circle at all, then the point C and D cannot be defined. So it may seem that this line is itself, this line segment is where it stops. But as it turns out, the polar of the point P is the full line. And if we were doing this question in a complex projective plane, in that plane, every line and every circle have points of intersection. So you'll find complex solutions to the equation if you solve them. Like if you take any random line through point P and a circle, they will intersect in a complex plane. And in that plane, again, if you take the harmonic conjugate, that point Q will come back and lie on this line Q. Okay. So there is this complex plane is something that we might study at a later point if we have time. It's a very interesting way of doing geometry. Okay. But so in fact the whole line AB is the locus of all points Q, such that the intersection points CD and PQ are harmonic. Okay, and there is another way of constructing this line Q, which may completely be surprising, but it works out very well. So if what happens if I join okay, unfortunately my diagram doesn't show it, but as it happens, there is a concurrency here. Okay, pardon the bad diagram, but if we do draw the diagram properly, you will see that the cross join. So by what do you mean by what do I mean by the cross join? I join point C with D1 and D with C1. Okay. This cross join also lies on the same line. And the parallel join. So by parallel join, I mean CC1 and DD1. They will also go and intersect on the same diagram, on the same line. So all of these concurrencies are happening in this diagram. The cross join as well as the parallel join meet on the same line, line AB. So what is the meaning of all of this? Interestingly, as it turns out, I mean, I'm not giving you the proofs of these facts, but we will look at the proofs of this when we do the poles and polars topic. But assuming that these facts are true, it gives a very interesting construction. Suppose I give you a circle and a point. Can you construct the points of tangency or the tangents from the point to the circle with a ruler and compass?
Yes.
Everybody can draw the
Yes, sir.
construct the tangents with a ruler and compass. But what I showed you just now is you can do it with only ruler also, because you can do this construction. You draw any two random lines. Okay. You'll do the cross join. Then this point lies on the line AB. And you can repeat this procedure for another pair of lines to point B, and you'll get another point, or you can do the parallel join here itself. So if I do the parallel join, so again my diagram is very bad, but this point also lies on the same line. So if I join these points together, these are my points of tangency A and B. So I could do the, of course that circle was given to me. I cannot draw a circle with a ruler, but given that circle, then the rest of the whole construction can be done with only ruler. I don't need a compass at all. And this is where the whole thing only starts. This is only the start. There is a theorem later on. Even I don't know the full. I may know, but I don't remember the full proof of this theorem, which says if you have a plane, okay, and you need one circle because you cannot work without that. So somebody has drawn one circle for you in the plane, okay, and you have only one ruler. You can do any construction in geometry which you can do with a ruler and compass. So ruler and compass are equivalent to ruler and one fixed circle given in the plane. With the help of this single circle, you can do every other construction which is doable with the compass also. So this is a big result. We may need to work towards it step by step. I don't think we have enough theory to do that, but we will do that eventually maybe. But all of this starts with this problem. The fact that, I mean, we can do the tangency with the ruler only, that itself comes from this fact. So that, I mean, there are like deep connections of this problem and a lot of interesting theory in geometry, which we will explore in the coming months. Okay. Yeah. I think then let's move on to the next problem. So this was question F. Question G. Okay, how many have solved question G already? Nobody. Yeah, it is a tricky question, I have to say. It is not very straightforward, but in a way, it seems very simple to state, right? It's just a quadrilateral, which is just four random lines, and their intersection points are being taken. So it seems a very straightforward diagram, but it's a very powerful idea. Okay, question G. Okay, so this is the diagram. Basically, the blue lines are the four sides of the quadrilateral, and so in general, when you have four lines, they will intersect in 4 choose to 6 points, right? So in general, when we draw, quadrilateral, we just draw the 4 points A, B, C, D. But really, if we want to draw all the intersection points of these lines, then we have to draw P and Q also. So this there is a name to this diagram actually. This is called a complete quadrilateral. Okay. And you understand why we are calling it a complete quadrilateral, because we are drawing all the possible points of intersection of these four lines. Okay. So a normal quadrilateral has two diagonals, but a complete quadrilateral has three diagonals in a way. Because what do you mean by the diagonal in a quadrilateral? You take two lines, they intersect at a point, let's say point A, and you take the other two lines and they will intersect at another point C. So when you join AC, you get one diagonal, and you can do that for three such pairs. So that's why you get three diagonals. And what the question is saying, that the midpoints of these three diagonals are collinear. So you have to show that these three midpoints are collinear. So this is my strategy. I want to use Menelau's theorem to show the collinearity. So obviously I need to find a triangle on whose sides these points lie. Otherwise I cannot use Menelau's theorem. So what triangle can that be? So obviously the three orange lines which I've drawn, they will form a triangle. Unfortunately, in my diagram, they may intersect somewhere outside, which is not a very good way to show. I mean, basically I can still draw this diagram in a schematic fashion. I'll get a triangle like this. So maybe before I draw both linear diagram, just to indicate in a schematic way what I'm trying to do here. So basically I'm interested in the points, let us call them x, y, z, okay? X, Y, Z. Okay, so these are the intersection points of these diagonals. And so now you see that all the three midpoints we are interested in, let us call them element. So they are clearly lying on the sides of this orange triangle. So numerically, if I want to apply Menelau's theorem, the ratio I want to prove is YL upon LZ into Zm upon Mx into Xn upon Ny equal to -1. If I show this, then I'm done. Okay, are you able to follow?
Sir, can
Yes,
you
sir.
please label the
You want to repeat the this question? So the orange lines are the diagonals of the quadrilateral, the complete quadrilateral. And so when we intersect them, we get the triangle XYZ. And what you want to show is the element points are collinear, and each point lies on one of the sides of this orange triangle. So that is why we can use Menelau's theorem, and we have to prove this statement. But if we prove that, then by Menelau's theorem we can say that the 3 points are collinear.
sir, which triangle you have used for Menelau's theorem?
Triangle XYZ. So because point L lies on YZ, M lies on ZX, and N lies on XY. Correct?
Yes, sir.
Yeah. So I'll draw this diagram again once more, then I think it will become a little bit clearer. In general, I know that this diagram is very hard to draw. You always get these kind of parallel lines, all parallel looking lines. So how to draw the diagram nicely in a given amount of space is a tricky challenge, I know. But maybe with some trial and error, I will get it. But anyway, but even before we draw that, I just wanted to give you the schematic that what is the overall approach we are trying to use here. Okay, so we want to apply Menelau's theorem. Now the difficulty is, so each of these ratios YL upon LZ, etc. They don't look very obvious. How are we going to compute them? That is the difficulty. For example, let us take one ratio xn upon ny. Okay, if I have to compute xn upon ny somehow, and the only information I have, so I know n is the midpoint of PQ. Okay, so I know that at least n is the midpoint of PQ. But still, how do we work out the details is the question here. So for example, on this line PQ, consider the ratio xp upon py, xq upon qy, and xn upon ny. These are the three. So basically, n is the midpoint of PQ. That is why I'm looking at these three ratios. So can I find some connection between these three ratios? Okay. So that's the first thing I want to try and find out. Okay. And by the way, what can you say anything else about the points x, p, y, and q?
So they're harmonic.
You see the points x, p, y, and q are harmonic because in this diagram there is Sevas theorem and Menelau's theorem happening simultaneously. This triangle PQD. Do you see that for triangle PQD, what this diagram is really looking like? This PA and QC are the Sevians, and when I join DB directly, I get point Y, and when I extend AC, this is point X. So this is really that Seva Menelau happening together in the same diagram kind of configuration. That is why PQ and XY are harmonic. So there are lots of interesting or other lots of interactions between various Sevians, Menelau's theorem, lot of things happening in the same diagram. Okay. So if these points are harmonic, what can you say about the ratio xp upon py and xq upon qy? They will be negative of each other.
Yes, sir.
Okay. Because see, important implication of cross ratio is that in the diagram, when x and y divide pq internally extending the same ratio, it also means p and q divide xy internally extending the same ratio. It is a symmetric way of looking at it. So from the Sevai-Menelau's theorem, here you will get py upon yq equal to minus of px upon xq. But the same thing you can rearrange and get this expression, that xp upon py equal to minus of xq upon q. Okay, so first thing, let us look at this part. Like this is a lemma, you can say, because I want to extract only this part of the diagram. Only this line I want to look at, because on this line something peculiar is happening, that the point n, which is the midpoint of the segment PQ. So let me just draw that part separately here, and I'll just also rotate the diagram for that. So what do I have? I have on this line points P and Q. Okay, their midpoint is n, and I have another set of points x and y. The viewpoint marks are a bit distracting. Okay, so given what is all given, that n is the midpoint of PQ, and they are harmonic. So PQ xy is harmonic, or equivalently, so I could write the ratio xp upon py equal to minus of xp upon qy. Okay. And we are interested, because we want to apply Menelau's theorem, so we are interested in the ratio xn upon ny in this diagram. Okay. So the question is, what is xn upon ny equal to?
So we can use the result of the first, I think, C1 we have done this.
Okay, what is the result?
Sir, there was midpoint k and harmonic points, then k into
Yeah, you're on the right track. Only problem is there, if you remember, it is a product, it is not the ratio, right? So there what we proved is ny into nx, sorry, ny into nx equal to np square. Correct?
Yes, sir.
Whereas here we are interested in the ratio. So interesting, but we are very close. So I don't know if there is some connection and we can finish it off right away. But they certainly seem to be close. Anyway, I don't know about that right now at least. How can we do this problem? So let us do it this way. Let me call the ratio xp upon py. See, anytime you have a question like this, it seems that there are lots of variables. So we want to reduce the variables to the bare minimum so that it is easier to compute everything. So I only want to keep the least number of variables, which is enough to describe the whole diagram uniquely to me, because I am not interested in anything else. So, for example, here one variable which I think is xp upon py. Whatever this ratio is, let me call this ratio k. Okay, xp upon py equal to xq upon qy. So, if you think about it carefully, if I give you this number k, that is enough to draw the whole diagram uniquely. Because what will happen if you consider starting with from the points x and y? Okay? So any points x and y you choose in the plane, you can uniquely, if I know this ratio k, then the position of point P is going to be fixed, and the position of point Q is also going to be fixed. And naturally, if P and Q are fixed, the midpoint N is also fixed. So the whole question can be written in only one variable, which is k. Do you understand that part?
Yes, sir.
Okay. So then let me just compute everything. Okay. So I am interested in the ratio xn upon ny. So if I compute the length of xn and the length of ny, then I will get everything I want. So I am interested in finding the length of xn and ny. Then everything will be done. So to find this, if I find xp and xq, then obviously xn is nothing but xp plus xq upon 2. So all I need to do is find xp and find xq. And can I do that? Because I know the ratio k, and I mean the length xy is also there in this equation. Actually, there is one more variable which is xy, but ultimately you will see that the xy factor will cancel out. So it doesn't really matter. But for temporarily, you can introduce that variable xy also. Let's say xy is equal to some length distance d. So in terms of d and k, we can do all the calculations. We can find out how much is xp, and we can find out how much is xq. So I'll give you a couple of minutes to try it out. Okay. So basically it is just a set of simultaneous equations, because what we have is, we know xp upon py equal to k and xy equal to d. So if I write this as k upon 1, I am interested in xp. So if I add the numerator to the denominator, xp upon xp plus py equal to k upon k plus 1. And xp plus py is nothing but d. Therefore, xp equal to d times k upon k plus 1. Okay. And what about x cube? So in the case of x cube, we have to subtract because if the point is outside. So x cube upon qy is again, so this will go to minus k this time. So minus k upon 1. So I am interested in xy in the denominator. So again, x cube upon x cube plus qy equal to minus k upon 1 minus k. And again, denominator equal to d. This is nothing but xy, which is equal to d. So I get x2 equal to d times minus k upon 1 minus k. So I have xp and xq now. So I can find xn, which is equal to xp plus xq by 2. So d will come common, d upon 2 times. In the bracket, I have k upon 1 plus k plus for other minus of k upon 1 minus k. And maybe I can simplify this a little bit to k minus k square. Okay, so ultimately xn is nothing but d times k square upon k square minus 1. And I'm interested in ny also, but ny can be quickly written as xy minus xn. Right. Remember, these are all directed segments, so that's why I can quickly, I don't have to scroll up and look at the diagram also to say, see where x, y, n are there, do I have to add, subtract, I don't have to bother with anything. I can directly write this equation confidently because I know everything is directed distance. So this is nothing but d minus the what I showed on the expression. So this is d times what will it be? 1 upon k square minus 1. Correct. Therefore, the ratio xn upon ny, what is the ratio?
So k square.
K square. So before we go back to the original problem, just take a moment to appreciate all the calculations we have done here. Okay, what was the starting point? Remember, all of this is happening on this one line. So this yellow line PQ, yellow or orange line. We are only doing this calculation on this line PQ, but by symmetry we can do the same thing on all the 3 lines. So we plan to use it that way, but focusing on that one line to begin with. So we knew that the 4 points x, y, pq are harmonic, and the n is the midpoint of pq. Okay, so we wanted to use that harmonic ratio with the ratio k. Okay, So this ratio k we wanted to use, and we wanted to find the value of xn upon ny in that term finally, because we want to use that in Menelau's theorem finally. Okay, and then that problem simply became a question of computing the distance xn and ny, and that you can do because we can compute the distance xp and xp, and that part is kind of straightforward. Yeah, I mean, this is a typical problem we do all the time. If we know the ratio and we know the distance xy, then we can find the individual parts. So I'll just leave this on the screen for a minute if you want to copy anything down. But the final conclusion we are interested in this, the fact that the xn upon ny is equal to k square, which is, by the way, nothing but the square of the original ratio. So it is nothing but xp upon py square. So really, this is the important part, that xn upon ny is equal to the square of xp upon py. Okay, so having understood these things, let us go back to the main question. What does this imply for us? What we want to show here really? Does this bring us any closer to what we want to prove or not? That is the question here. So in this diagram, xn upon ny, this term from what we showed right now is xp upon py whole square. And by the way, there's nothing special about point P. This is also equal to xq upon qy whole square. I mean, the xp and py and xq upon qy have opposite signs, but when you're taking the square, it doesn't matter.
Yes.
So similarly, how can we rewrite the other ratios also? So for example, look at yl upon lz. Yl upon lz, if I do the same thing on this line, okay, now I'm talking about this line. So what will that be equal to? Okay, let me just fix the diagram. This point z, it's not clear where the point m is and point z. So let me just redraw that part a little bit. Okay, so this is our point z, and the midpoint m may be somewhere here. Okay. So yl upon lz.
So can we tell it similarly yb upon yd the whole square?
Exactly. So it will be equal to what? Can you repeat?
Yb upon yd the whole square.
Is it yb upon yd? Look at this part carefully.
Yb and upon bd, sir.
BD. It should be BZ, right? See, the 2 points here, x and y are fixed. So starting and end point of your ratio is always x and y.
Okay, sir. Yes, sir.
Okay. So what should I write?
So yb upon bz the whole square.
Yb upon bz the whole square. And then the remaining term. So zm upon zm upon mx. So on this line, zm upon mx equal to
zc upon cx the whole square.
zc, or I can
P upon CZ whole square.
yeah.
Yes, sir.
So instead of c, let me use point a. Okay, so za upon ax whole square. Okay.
Okay, sir.
And so here also I could use point P or Q, either of them, but let me use point P. So now what happens if you put everything together? Do you see what is happening? if I multiply all these three things together, the square will also, of course, come out common. So what will be remaining inside the square? So x, so the original product, right? If I call it star, then the star is equal to yb upon bz into za upon ax into xp upon py whole square. Okay, so I've just taken the whole square outside. So isn't this equal to -1, the part inside the bracket?
Yes, sir.
This is equal to -1 because this is nothing but Menelau's theorem for this segment, this line PBA. This is simply Menelau's theorem for this line.
Yes, sir.
Okay. Okay, so then is there some mistake here? Because
So then the square will become 1. So 1
yeah, the square is becoming 1. Let me think if I made some mistake somewhere. Oh, you know what? I think there is a mistake in my original. Can you check this? I think this is equal to minus k square. Can you just check closely?
Okay, so 1.
I think that is a mistake. Let me just redo this calculation once more.
Yes, sir, it is minus k square.
I think while writing the ny we made a mistake. So ny equal to, this is d minus xn, which is d times k square upon k square minus 1. Okay, so this is d, if I take d common, I get k square minus 1 minus k square upon k square minus 1. This is equal to, yeah, so this is minus 1 upon k square minus 1. Okay, so the ratio is minus k square. Okay. Yeah, good that we caught this mistake. Okay, so then I think then this fixes the problem, because then there will be one minus sign coming from each of the three brackets. So every place there is a minus 1, minus 1. So when I multiply everything together, there will be one left over, basically will be minus 1 cube, which is equal to minus 1. So the whole product finally ends up becoming equal to minus 1. Okay, did you follow these last steps what we did? And after we
Yes,
obtained
sir.
the fact that each of these original ratios can be written as minus k square form, where the k is the individual ratio. For example, for xn upon ny, it was xp upon py, etc. And then when we multiply them together, we have one last use of Menelau's theorem in the triangle xyz. Okay, again we are applying Menelau's theorem in triangle xyz only, but with the transversal PBA, because then the points PBA are already given to be collinear. Yeah, so I mean, yeah, as I said, this was not a straightforward problem as such. I knew that, but you understand that how in a one big problem there are several small problems. So when you put those parts together, you get the big problem. So here, if I split this problem into the separate parts, like if I ask you to prove that xn upon ny equal to minus xp upon py whole square. So if I ask you to just prove this part, I think many of you would get it. But the difficulty in an Olympiad problem is that you have to look at these, find out these individual parts that they are hidden there, and to do that, you have to rely on some motivation. For example, here the motivation for me was I want to show that points LMN are collinear. So if I am interested in collinearity, I have to apply Menelau's theorem. But if I want to apply Menelau's theorem, I need a triangle on which these 3 points lie. So looking at the diagram, the most like symmetric choice would be this orange triangle, triangle XYZ. Okay. So then going to the next step, if I want to apply Menelau's theorem, I need to find the actual values. I need to find xn upon ny. Okay, but to do that, what is the information I know already on this line? So I know that xp, yq are harmonic. and n is the midpoint of PQ. So based on just these two factors, I should be able to find xn upon n bar, which is what we did here, all this calculation. And by the way, I mean, this calculation is useful for you as a permanent resource, that anytime you have this configuration where you have harmonic points and one of the midpoint of the one of the segments, you know what that ratio is going to be like. So in general also, this is a good thing to store in your bank, let's say. Then having computed that it is equal to minus k square, we come back to the original problem and we are able to rewrite the original three ratios as the minus k square form on the three respective lines. And then finally, we didn't know this, by the way. Luckily, it turns out that there is a Menelaus theorem here. If it turned out that these ratios are not very nice or there is nothing we can, nothing useful about it, then this whole approach would have become wasted. But thankfully, the everything, the stars aligned, and the final product also turned out to be Menelaus theorem. So all of these 3 or 4 different parts were put together to solve this problem. But each step had some motivation. It was not like out of the blue. I mean, I don't want to take away from these problems or lectures that if I can't think of this idea, then how will I solve this problem? So you have to overcome that hurdle. You have to, and that will happen with practice. I don't expect that within just a few days you will start to get all of these insights. But the more problems you solve, the more time you spend to understand the motivation behind each step. Even if you are not able to solve a problem, after you look at the solution, appreciate how that solution arrived. What was the motivation behind every step? That is what will help you to become a better problem solver. Just looking at 1,000 problems and reading their solution like a storybook will not help you at all. Okay, so it's important for you to put in the work to analyze every problem. Okay, any doubts about this part?
No, sir.
Okay, so as it turns out, there is one more proof of this question, and that is the proof which, if you ask me, is the more divine intervention, where somebody thought of this idea, and that is how that proof worked out. Or I don't know, maybe whoever thought of that solution first, maybe they also had some motivation in their mind. We cannot assume that they just got that idea through inspiration. But anyway, this is the solution, and this is also a very interesting solution. But don't ask me why is this solution supposed, I mean, why this solution works is fine, but why should you think of this solution? I don't have an answer to that question. In a way, there is one takeaway from this solution which I will mention, that whenever you have midpoints, right, you should think of parallel lines. This is something which we also have talked about before. Whenever you have midpoints, for some reason there is a lot of cross connection, like it all comes from the harmonic range kind of thing, or I mean, there are multiple reasons for that. But whenever you have midpoints, you should think of parallel lines. So the idea is this. For the labeling BCD. Let me call these points element. I want to show element are collinear. Now L is the midpoint of BD. Right. So okay, let us look at the parallelogram. Okay. For which BD is one diagonal. Okay. So for example, I could consider, so I'm drawing a line parallel to the base. And this is parallel to this thing. Okay, so I constructed a parallelogram like this. So clearly L is the midpoint of DE also.
Yes, sir.
Okay. And I could do the same thing for other 2 points also. Oh, sorry. I think I made a mistake. I want to do this parallelogram idea, but and point L is already nice. Okay, yeah, that was the thing. Sorry. So point L is already nice. By nice, what do I mean? BD, it is already lying on the line BD. I want to do this parallelogram idea for point M and N. So for point M, yeah, okay, I got it. This is the idea. Point M is the midpoint of AC, but AC has no connection with BD. That is the difficulty. So I want to connect the M with line BD. So to do that, I have to choose a different segment for which M is the midpoint. And for that, I construct this parallelogram. So I complete the parallelogram CDA. So CDA and some other point will form a parallelogram. Let me call this point D dash. And just call it point T. I don't have a better name for it. And it will not be like this somewhere over here. Even after months, I'm struggling with this basic how to use this tablet. But anyway. So I completed this parallelogram CDAT. And now you can see that M is the midpoint of AC and M is also the midpoint of DT, correct?
Yes, sir.
I think next year when I take this lecture, I'm going to use GeoGebra at least for this part. Okay, that is good. Now let us continue. Let us do the same thing for point N also. So point N is the midpoint of PQ. Again, it has no connection with other points. So I want to construct that parallelogram. Okay. So again, I complete the parallelogram PDQS. Let us see. And so N is the midpoint of SD. This is a nightmare to draw. I'll just write it. N is the midpoint of SD. So the points L, M, and N, what are the midpoint of? L is the midpoint of DB. M is the midpoint of DT, and N is the midpoint of DS. So do you see, if I want to show L, M, N are collinear, what is an equivalent statement?
DBTS.
BTS are collinear. BTS are
Yeah, if BTS are collinear, then obviously L, M, N are collinear because by midpoint theorem, that everything is basically parallel to the BTS. So I still have to show BTS are collinear, so I'm not done. But this is what I can do now. Actually, in hindsight, I feel that why am I even telling you this proof? Because there is not much instructive value, to be honest. It is just that this is an interesting proof which exists. So that is the only reason why I'm telling you this proof. It's not, I don't see any interesting value in it. Okay, so let us look at this light blue parallelogram which I drawn just now. Okay. And we can label its point something B, S, some other variable which are not used so far, K and L. Well, I used already, J and K. Okay, so look at this parallelogram BKSJ. I am interested to show that BTS are collinear, which is to say T lies on the diagonal PS. So I want to show that T lies on the diagonal PS in this parallelogram. So as it turns out, there is a property. So this is a separate lemma that if you have a parallelogram and if you take any point on the diagonal, okay, and I draw the lines parallel to this parallelogram like this, okay, so I get two areas here, this area and this area. So as it turns out, these two areas are equal in area. These parallelograms are equal in area, I should say. Okay, so the property is in fact if and only if, that if I do this for any point P, okay, and I construct these parallelograms like this, if I call this parallelograms A1 and A2, then the property is that P lies on the diagonal BD if and only if the area A1 equal to area A2. Okay. I don't know if you have a chance to look at this lemma earlier, but if not, I mean, it's just a useful property to know. If I mean, that is the one takeaway from this question, you can say. And I'll leave this as an exercise for you to prove that if P lies on the segment BD, then the area A1 and A2 are equal, and vice versa.
Sir, it's by Pappus theorem.
Pappus theorem, okay, yeah. I think there is also Menelaus or some simpler proof may also be there, but yeah, it can be done. Okay, so given that this lemma is there, in the given diagram, you want to show T lies on segment BS. So it is enough to show that these two areas are equal, this area and this area. Then I'm done. So where are these areas equal? So in the area of a parallelogram can be represented as the product of its two sides into the sine of the angle in between them. So basically, a triangle is half AB into sine C. Parallelogram is simply AB into sine C. So because everything is parallel to our starting original two distances, so that's why I think we can say that the angles are equal here. So we are only interested in the product of the two sides. So this
Sir, if
is
we join the one of the diagonals of the smaller parallelogram, then
okay.
by it will be half of both the no sir, the other one below it.
This one.
No sir, the between the two, the smaller one.
This one.
Yes sir.
Okay.
So the area of that triangle will be half of both the parallelograms. It will be equal.
No, I don't follow that because basically the area of this triangle is half of this parallelogram. But how is it connected to the parallelogram above and to the right? Because won't these ratios matter? Like how far is this side from this one? Okay. Anyway, I am not able to complete this proof right now. I mean, suffice
They
to
are
say,
between the same parallel lines, right? So the height will be same.
height is same, but what about base?
Yes.
Okay. Anyway, I mean, I think I saw this proof in some textbook. I can just forward you that link later on the WhatsApp group. I am not able to work out the details. Maybe I missed something. Maybe the choice of the parallelogram was wrong or something. But at least this is the motivation. But yeah, as I said, like there is not much learning value from this question directly, this solution directly. But anyway. But I mean, compared to this, the first solution, at least I feel that there is a clear guided way of approaching the problem. And I think there might be another solution also based on cross ratio, but I'll need some more time to work it out. Okay. Any other doubts on this question? We can move on to the next one. Okay. So this was question G. Okay. Question H is from IMO 1993, question 2. So if you have not spent enough time on this question H, then I don't want to reveal the solution because again, there might be some, even if you're not able to get the whole question, you might make some partial progress, and that is exactly what I want for all of you to try. So if you not spent enough time on this question, I want to leave it for now. I mean, right now I have 25 minutes left in the lecture. So maybe I want to use this time to just fill out the gaps. Like there are some things in the theory which I maybe missed to mention, or I need to highlight even more. So I want to spend time on that. Okay, so for you, question H you can try at home. If you don't get it, I'll I mean, actually, this question is available online, so you can always look up the solution on any forum or anywhere. So it is not hard to find the solution to this. Let's see. Next time, if I anyway, I'm going to conduct the test. But if I have some time left over after the test, then we can discuss the question H. Okay, so we will leave it for now. Okay, so then, yeah, as I said, let me just recap some of the things that we have done so far for both the topics, cross ratio as well as poles and polars. Some important sort of keystone, which are the important properties that you have to keep in mind. And based on those properties, you are going to find a lot of cross connection between the topics. Okay. So for power of a point, I think the most important concepts are radical axis. The fact that any two circles, if you take the radical axis is the common the set of points which have an equal ratio, and when you have three circles, you get a radical center. So the radical axis and radical center are the most important parts to understand from power of a point. Okay. And another important thing I think which we used in one of these questions was the fact that you can treat a point circle, a point also as a circle of zero radius. I think one of the questions about orthogonality we had used that idea. Okay, so important to think of the single point as a circle of zero radius. And another thing about radical axis is that basically the radical axis bisects the tangents. So if I have a radical axis of two circles, then the common tangents, this point will be the midpoint of this, because obviously the power of this point is going to be equal, pt1 square equal to pt2 square. And this is true for all the four tangents. So you have two direct tangents and two inverse tangents. For all the four tangents, as it turns out, the radical axis is the midpoint, or rather bisects those four segments. Okay, so this is one important corollary which I think we didn't properly mention earlier. Okay. Then I mean the finding the distance of this radical axis, that part I think we already done, so I don't want to repeat that. Anything else worth noting? Obviously, for circles which are intersecting, the radical axis is the common line, common chord rather. Okay. And for this reason itself, when you have three circles which are intersecting, their pairwise common chord are concurrent, but it is true for even the radical axis which are not intersecting. Okay. Then closely related to this last property about the radical axis are the coaxial circles, because what happens is that basically any point on this line, radical axis, can be the center of a circle. So from this point, if I draw a tangent to any of the two circles, obviously the tangent length will be equal. But not only that, if I choose that tangent length as the radius, then I can draw a circle, and that circle will be orthogonal to each of the given two circles. Okay. And if I keep doing this for every point on this radical axis, then I get another family of circles, and that is the coaxial family of non-intersecting line. And for that family, I mean, you can imagine the diagram as this point, this center moves closer and closer to points A and B. Okay. So if that point P is taken very, very close here, okay, then the length of the tangents also keep on reducing. So ultimately, in the limiting case, point A itself becomes a circle of radius 0, and same with point B. Okay, so these are the two limiting points of this family. And for this family, the radical axis is the line joining the center, this O1O. Okay, so this duality of the two diagrams is very important in coaxial family. So I think we have spent enough time on that again, so don't want to repeat that. Okay, and I think this question 2 keeps on occurring again and again. The fact, I mean, we saw the same property in a different context in the cross ratio topic. How when you have four harmonic points, the product is equal to the R square. So that is the same thing being repeated here. Nothing new about that. But yeah, I think the most important takeaway from coaxial is that Apollonius property. So the question 4, I think if you remember, we spent a good amount of time working on the calculations of when you have three circles of the same coaxial family, how one of them is the Apollonius circle for the other two. So, and that is what we use even right now. Then among the questions, I think question 8, which was the area of the pedal triangle, that was I think an important part. And we are going to see connections of that with the Simpson line also later on. Okay, I think these are the important highlights of coaxial family, which I remember. Yeah. By the way, yeah, question 5. Yeah, let me complete this one. Jaydeep, I think, has been waiting for a long time for question 5 solution. So let me just give you that one. Apart from that, in fact, in these problems, right, question 3, which is Carnot's theorem, is a very important property. It can help you to find a lot of concurrencies when you have perpendiculars to be shown to be concurrent. Okay. So understand question 3 properly. Okay, question 5. Let me just quickly explain what is the diagram. By the way, Jaydeep, did you get the solution to this on your own in the meanwhile?
No, sir.
Okay. Okay, so what we have is triangle DEF, and we want to construct perpendiculars to the sides. Let me just keep it. Okay. So from A, I want to construct perpendicular to EF. So by the way, what is that perpendicular line? Can you say? Is there another way of writing what is that perpendicular line?
Sir, AO.
It is AO. Okay, so I think we visited this part also earlier. That basically the isogonal conjugacy means that the AH and AO are symmetric with respect to the angle bisector of angle A. So this is our point P. And similarly here, so instead of saying the altitudes from ABC, I can just say I am talking about the lines AO, BO, and CO. So let me call this point Q, and this is R. And the question seems quite tricky because now, I mean, we are not even done with drawing the diagram, because now what I am to show is that the perpendicular from P to BC, Q to CA, and R to AB, perpendicular line. So these three I have to show to be concurrent, and in the diagram it seems very hard to even draw them properly. But thankfully, this is where Carnot's theorem helps us, because it's enough to show that PB square minus PC square, so this kind of cyclic summation, I have to show that this sum is equal to 0, then I am done. So the difficulty here is how do we compute this sum, because again PP square minus BP square minus PC square doesn't seem directly tractable. So the trick we can use here is we can do a bit of regrouping. Basically, I want to put in this diagram, I think AP and PQ are the most clearly visible. So let me focus on those. So which are the terms involving the points A, P, B, and Q? So I have BP square.
Sir, but we have to consider perpendiculars from PQR to BCCA AB.
Yes. So I mean, what is the Carnot's theorem? What is, if you go back to the statement of Carnot's theorem, isn't that the same thing? So let me again illustrate what is Carnot's theorem. What Carnot's theorem says is that it's actually very nice result, that if you have a triangle, okay, and you have any points here, oh, okay, I understand. Actually, there is a small gap in the what I've given in the sheet as Carnot's theorem is not really Carnot. It's a special case of Carnot theorem. Carnot theorem is a little bit more general, but anyway, I'll just illustrate what is happening here. So suppose let's take the special case between. So PQR lie on the three sides, and I am talking about these three perpendiculars. So what Carnot's theorem says is that these three perpendicular lines are concurrent, and it will not draw them to be concurrent. Okay. So let us say they are meeting somewhere. So they are concurrent if and only if this statement, whatever I wrote, PB square upon PC square, this summation equal to 0. So this is Carnot's theorem. And so what is the proof of this? Suppose any two of them intersect, okay, at some point k. It's the same thing which we use all the time. So basically PB square upon, you can write two of these values. So BP square minus PC square is equal to nothing but BK square minus KC square, because I am able to transfer the ratio, the difference of the squares anywhere on this line, it will be constant. Similarly, CQ square minus QA square is equal to CK square minus KA square, right? And if you add them up, what happens basically, and the last one which are interested in AR square minus RB square. Okay, I want to show that if, let's say, if the three lines are concurrent, then I will get this. Okay, because then all of them are passing through point K. So if I add them, obviously the RHS is equal to 0 because it is simply BK square, CK square, AK square, they will cancel out. And the LHS is equal to 0. Therefore. So this is the forward part, and the reverse also you can do in the same way. So this is Carnot's theorem, the another special case of Carnot's theorem. Now the leap that you can take is, there was no reason to take point PQR on the sides of the triangle. They could be any points in the whole plane. So the exact same statement is true even if I have point P somewhere here, and I drop this altitude. Okay, point Q somewhere here, I drop this altitude, and point R somewhere here and drop this altitude. Okay, so for these kind of floating points also the same thing is true. Again, BP square minus PC square plus that whole cyclic summation. This is 0 if and only if these three lines are concurrent. Okay, I call these lines L, M, and N. So this is Carnot's theorem. But do you see why this theorem is obviously true if the first one is true? Because again, the point P, I could take the point P1 over here. So for P1, Q1, R1, we have already shown the proof. And obviously BP square minus PC square is equal to P1 square minus P1C square. So that is why each of those terms can be replaced by the equivalent point on the sides ABC. Okay, so the special case of Carnot's theorem is not that special, it is just a simplification. Okay, so with this background, if you understand this background, now going back to the original question, we want to show that the perpendicular from P to BC, okay, etc., those three are concurrent. So now do you understand why it is enough to show that this sum is equal to 0?
Yes, sir.
Okay. Yeah, actually I went through this part a little bit fast, but anyway, I don't, the Carnot's theorem is not a really big highlight of the theory which we are doing. Okay, so anyway, coming back to this calculation. So we want to show this sum is equal to 0. So I'm interested in the points A, P, B, and Q. Okay, so I want to regroup this in a way where I isolate, let's say, PB square and AQ square. Okay, so I just want to look at these two terms. Okay. So basically, I am interested in PB square minus QB square. And cyclically, I could write similar terms for the other ones. So in this diagram, there are some similar triangles which we can use. In particular, if you look at triangle AFP and triangle BFQ. Okay, you see that this angle, which is equal to C, is equal to this angle, and obviously there is a 90-degree also. So do you see these two triangles are similar? AFP and BFQ are similar. What that allows me to do is, basically I want to use cosine rule. I want to find the length of BP and QA as with cosine rule. But the cross terms of that are going to be equal because of this similarity. So for BP in triangle BFP, by cosine rule, how much is BP square equal to? BP square is BF square plus FP square minus twice BF into FP into cos of angle BFP. And QA square equal to, so in triangle QFA, QF square plus FA square minus twice QF into FA into cos of angle AFQ. Okay, and I have to subtract these two. So again, I'll leave out the details for you to work out because we don't have enough time. But because of this similarity, you will see that obviously these two angles are equal, but this product BF into FP is equal to QF into FA. You can get that from writing the similarities of these two triangles. So when I subtract one from the other, this term simply cancels out. And so what I'm left with is BP square minus QA square equal to this part, BF square minus FQ square plus PF square minus FA square. And I could do the same thing cyclically for all the three sides, all the other three pairs. So ultimately what I will get is, so this is BP square minus QA square. Similarly, I get like the cyclic terms here. But on the right side, what I will get, BF square minus FQ square. And this pattern will continue. Oh, sorry. I think I regrouped them in the wrong way. I am interested in not BF square minus FQ square. Actually, I am interested in, yeah. So I'll put FA here and FQ here. Now in the diagram, do you see how, yeah, I don't know how to write it out. BF square minus FQ square, BF square minus FA square is referring to point F lying on line AB. And if I write the cyclic terms like AE square minus EC square and CD square minus DB square, their sum is going to be equal to 0 because these three perpendicular lines are already concurrent at the orthocenter. So cyclically, this first kind of sum will be 0. And similarly, cyclically, the second kind of sum will also be equal to 0 because of the fact that AO, BO, CO are concurrent at point O. So FQ square minus QD square, and cyclically if I write, that sum is also equal to 0. So basically it is two applications of Carnot theorem. One, this is a Carnot theorem for triangle ABC and point H. And this is Carnot theorem for triangle DEF and point O. Okay. So yeah, this is the overall schematic of this solution. I didn't get enough time to work out all the details, but I hope you got the general idea. So you can try to work out the calculations. Is that fine?
Yes, sir.
Yeah. Okay. Yeah, this was a hard problem, I have to admit. I mean, but yeah, I mean, the last problem of any problem sheet you can expect to be a hard problem. There's nothing about that. Okay, so then moving on to the cross ratio topic, I think there is not much additional to be said. This question 6, let me just, or rather point 6, let me just give you the definition. So actually it is nothing but, so far we have been talking about harmonic objects on a line or four concurrent lines, but we can transfer that ratio to a circle. That is what this is. So if you have a circle and some point P, and through this point P there happens to be a set of 4 harmonic lines. Okay, then wherever they intersect the circle, these points A, B, C, D, they are called a harmonic quadrilateral. Okay. And the advantage of this is again similar to what we have been saying all the while, that why cross ratio is important. Yeah, we can transfer the ratios. So like for example, to begin with, why are these 4 lines harmonic? Maybe because there is some transversal which is having the harmonic point. So these 4 points maybe internally, externally are being divided in the same ratio. That is why these 4 lines are harmonic. Then if ABCD is a harmonic quadrilateral, now it doesn't matter which point P you take. If you take another point Q here, then QA, QB, QC, QD are also going to be harmonic. And then on those 4 lines, again, if you have some other transversal, they will make another 4 set of harmonic points. So like that, you can keep transferring the ratios from here to there. So that is all there is to it. You can the fact that the 4 lines are harmonic gives us some values in terms of sign. So the sign of alpha upon beta, etc. So some quantity you can get in terms of the angles here. So the same condition can be applied for the 4 points on the circle. So yeah, I mean, I don't know if there is anything more to be said about this property. Okay, and yeah, one last thing I want to mention about the cross ratio, like I realized this when I talked about the midpoints. So when I keep on saying that midpoints and parallel lines are related to each other. So why is that? So that is because of the fact that suppose you have points AB and the midpoint C. So what is the harmonic conjugate of point C on this line? In other words, what is the point D such that AC upon CB equal to AD upon DB? So clearly you can see that the point D cannot exist on this line,
Yes.
right? But in the sort of extended version of the plane, like the projective plane, we invent a point at infinity. Okay, so there is a so-called a point at infinity, P infinity, or I don't know what is the symbol for that. So in a way, you can say that there is a point at infinity, which is the harmonic of points. Okay. Now, if you take any 3 lines passing through this, okay, again the same question is going to be asked, that for these 2 lines, what is the harmonic line of this line? So as it turns out, it has to be this line. But P is at infinity. So what does this make this line? It is parallel to this line. So in other words, this is the median and this is the line parallel to the base. So these 4 lines are harmonic. Okay. So PA, PC, PB, and PK. PA, PB, and PC, PK are harmonic. That is why the midpoints and parallel lines are connected. And now, because of all the theory we have developed so far, everything happens similarly. Now, again, if you have any transversal, these 4 points are going to be harmonic in a normal sense, etc., etc. Okay. So this is like one more connection between midpoints and parallel lines that we can explore. Yeah, I think that is all I have to say. Unfortunately, we are out of time, because I would also have like to spend some time explaining what is the implication of A and B. I mean, point A is simply an extension of this problem. So question A, 1A, which we did, said that if you have any 2 points, then the ratio AP upon PB uniquely defines a point on that line. In the same way here, if you have 3 points, then the cross ratio defines the 4th point uniquely. So it is just an extension of that. And point B is just understanding how, if you have 4 points, I mean, how many ways are there to create this kind of pair of 2 points and 2 points? So all of those pairs are related to each other, and in particular, the last one is quite interesting. That if you keep point A fixed and you keep rotating the other 3 points cyclically, then the product of all three you get is equal to -1. Yeah, I think yeah, that's all I have to share today. Unfortunately, we don't have time for a puzzle today. We can do that next time. Yeah, so as I said, you will have a small test next time. It will be partly numerical and partly subjective writing also. So and it will be based on these topics only, what we have done so far. So yeah, all the best for that. Thank you. Bye.
Bye.
Thank you, sir. Bye.
Bye, sir. Thank you.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you. Bye.